Question number 1. The rotation of molecule can be represented by the motion of particle moving over the surface of a sphere. Calculate the magnitude of angular momentum when L equals 1. So from rigid rotor, the angular momentum magnitude is calculated by h bar square root L plus 1. So you just plug into this L equals 1, and you can calculate the magnitude of angular momentum. And the possible component of angular momentum along z direction. So the z direction angular momentum is determined by quantum number m. So m times h bar. All right. So you need to find what the possible m's you have. M and L. M is determined by L. So in general, M is 0, positive, negative 1 until positive, negative L. Okay, so if L equals 1, then M can be 0, positive, negative 1. That's all. And then plug in this equation. You can calculate LZ. So here is the general relation between L and M. You have given L, you have 2L plus 1 M, and that is 0, positive, negative 1 until positive, negative L. And this illustrates the relation. So for a L equals 2 in this case. And so M can be 0, positive, negative 1, positive, negative 2. Now in this case, when L equals 1, then the only possible value is this 3, 0, positive, negative 1. Okay, that's all. So now plug in this equation. In this equation, L equals 1. Okay, so this is 1, and therefore you get 0 h bar times square root of 2. And plug in the number of h bar, you get 1.49 times 10 to the minus 34. Okay, h bar, remember, is h divided by 2 pi. Similarly, the z component, you plug in the m, which is here. So 0, positive, negative 1. And that gives you 0, negative h bar, positive h bar. And that's the value of the z component. Question number 2. What is the degeneracy of a molecule rotating with J equals 3? Now scientists like to use J or L to represent angular momentum quantum number. So here quantum number, angular momentum quantum number is 3. And the question is, what is the degeneracy? And we know that for a rigid rotor, the energy here, L plus 1 divided by 2I. So the energy is determined only by quantum number L. Okay, under a given L, you may have different quantum number M. Okay, so in general, when you have a given L, you have 2L plus 1 M. All right, and therefore you expect to have 2L plus 1 wave function, because wave function is determined by quantum number L and M. And so you have so many wave function, but they have the same energy because the L is the same. And that's called the degeneracy. So we have different wave function, but the same energy. So in this case, when L equals 3, and what's the possible M? It can be 0, can be positive, negative 1, positive, negative 2, positive, negative 3. These are the possible M. Altogether is 7. You can use this equation to calculate 2 times 3 plus 1, that's 7. So 7 wave function. Okay, they all have same L, different M. All right, and therefore 7 wave function, same energy. And that's called the degeneracy. So the answer is 7. Okay, next question. Both harmonic oscillator and the rigid rotor has quantized energies. So this is vibration, harmonic oscillator. This is rotation for a rigid rotor. And the question asks you to derive equation to show the energy for vibration equally spaced. For rotation, depends on J or L. It depends on L. Okay, so how do you do that? We choose two energy levels. So, for example, for vibration, we choose two arbitrary energy levels. So, for example, just N. And then the next one will be N plus 1. We calculate delta E, and we can show this delta E has nothing to do with N. That tells you the energy are equally spaced. They are all the same because it's independent of quantum number N. So let's calculate for N plus 1, the energy En plus 1 using this equation, and you have h divided by 2 pi square root k over mu, and now the N should equals to N plus 1. So N plus 1 plus half, that's 3 over 2. Okay, so for En, you copy this equation. So h divided by 2 pi square root k over mu N plus half. So use En plus 1 minus En, okay, that h divided 2 pi square root k over mu, and they all have this, so you factor out, and then use N plus 3 over 2 minus N plus half. So N cancel, and 3 over 2 minus half over 2, that's 1. And so that's the answer. Okay, you see the energy separation is independent of quantum number N. Okay, no quantum number N, and therefore they are equally spaced. Okay, all the energy separations are the same, this equation. Okay, so that proves harmonic oscillator energy separation are equally spaced. Similarly, you do the rotation. Okay, you choose L and L plus 1, and you calculate the EL plus 1 minus EL. Okay, and you will find that the energy has equation has a quantum number L in it. In fact, L plus 1 is still in the equation, and therefore the energy separation for rotation depends on L. So in fact, so when you increase L, the separation increase. So this increasing larger separation. And so what's the consequence? The consequence is for vibration, because these are equally spaced, they give you same frequency. In other words, when you do absorption line, you only see one line because they are the same. But for rotation, this is smaller, this is larger, and this is increasingly larger. So you will see many absorptions. So you will see a lot of absorptions for rotation. Okay, but in fact, we see these are absorption frequency are equally spaced, which are 2b. Okay, we'll have a question about this later. Question number 4. This is about diatomic molecule hydrogen iodide. So you can treat this as a rigid rotor model and ask you to calculate the reduced mass, calculate the moment inertia, calculate the energy of the first two rotational energy levels, and the energy difference between these two energy levels. So basically, we are going to use this equation to calculate allowed energies. But before we do that, we need to take care of moment inertia. And to calculate the moment inertia, we need to calculate reduced mass. And therefore, step by step, we first calculate reduced mass, M1, M2, M1 plus M2. But this M is the mass of one atom, so hydrogen atom and iodine atom. Now, if we use molar mass, then you need to change to one atom. So you can divide by Avogadro's number and then change to kilogram. Okay? Or you could use a conversion factor we used before, and that give you 1.65 times 10 to the minus 27 kilogram for reduced mass. and then you times R squared, in this case is 160 pm. Pm is 10 to the minus 12. So 160 times 10 to the minus 12 is 1.6 times 10 to the minus 10. Square it. Okay, so this is a reduced mass. So now we are ready to use this equation. And what is J? Well, it asks you to calculate the first two rotational energy level. So what are the possible J or L? Okay, the lowest one is J equals 0, and then 1, and keep going. So here, when J equals 0, the energy is 0. When J equals 1, so 1 plus 1 is 2. 2 times 1 is 1. So that gives you this times 2. All right, plugging everything. And here is the energy. All right, what's the separation between these two? So use this one minus energy for J equals 0. Okay, now if you compare the energy for vibration, you can see this is 2 orders of magnitude smaller, and that's falls in microwave range. So vibration energy higher is in the infrared, but the rotation is lower energy, it's in the microwave range. Question number 5. The moment inertia for methane is given. What is the minimal energy needed to start the rotating? According to rigid rotor, the allowed energies are h bar squared divided by 2I times L plus 1. L can be 0, 1, 2. So the lowest energy for the rotation is when L equals 0. That's allowed lowest energy. But however, when L equals 0, this will be 0. And therefore, this is not rotating. It's motionless. And so the lowest rotating is actually when L equals 1. And so in order to calculate the minimum energy to start the rotating, okay, we need to calculate the energy to go from 0 to L equals 1. So that means we calculate the energy of L equals 1 minus when L equals 0. Okay, and so when L equals 1, so put in here, so 1 plus 1 is 2, so you have h bar squared divided by 2I, and here you times 2, and the minus actually 0, so this cancel, you have h bar squared divided by I. Okay, and I is given moment inertia. Okay, so plug in, and that's the answer. Question number 6. Calculate the frequency of transition from 3 to 4 in the pure rotation spectrum of nitrogen monoxide. Now, the rigid rotor model tells us the energy is not equally spaced. So let's draw a few of them. All right, so this is J equals 0, 1, 2, 3, 4. And so you go from here to here. Okay, and we want to calculate the transition in the frequency from 3 to 4. Now, one way to do it is to use the energy equation E equals h bar squared divided by 2I j plus 1. So you calculate the energy of J equals 3, you calculate the energy of J equals 4, and you calculate the difference. And because it asks you frequency, so you let the difference delta E, okay, delta E to be h times frequency, and then you calculate the frequency. So that's one way to do it. The other way is that we already know the equation. For example, in question 2, you are asked to derive equation to calculate the separation to show the energy separation depends on J, right? So we already derived equation. In fact, in the class, in the lecture notes, okay, we also derived the equation that is 2b times J plus 1. That's the separation between any energy level as a frequency. Okay, so that's the general equation. And what is B? Well, first, what is J? So in this case, J is from 3 to 4. So you plug in 3 here. So 3 plus 1 is 4. 4 times 2 is 8. So it should be 8 times B. But what is the B? B is rotational constant, and which is defined as h divided by 8 pi squared times I c, speed of light. And so in order to calculate, to use B, we have to calculate the moment inertia. Just like last question, we need to calculate reduced mass, we need to calculate the moment inertia, and then we can calculate the B constant. All right, so B's constant here is inverse centimeter as the unit. And then goes to this equation, 8 times B. All right, that gives you 13.6 inverse centimeter. And this is in microwave range for the rotation. Now, the question also asks you, would the frequency increase or decrease if centrifugal distortion is considered? So all these calculations are based on rigid rotor where the bond length doesn't change. But if bond length change due to the centrifugal distortion, the distortion always stretch the bond length, becomes longer. So if bond length becomes longer here, R becomes larger, the moment inertia increase. If moment inertia increase, then the rotational constant decrease because it's divided by I. So B decrease, and so 8 times B will become smaller, and therefore the frequency, all right, you measured must be smaller, all right, than the rigid rotor predicted wavelength frequency. Question number 7. Indicate which of the following molecules show pure rotational absorption in microwave. Okay, so one of the selection rule for rotation absorption is molecule must be polar. Okay, now remember vibration is the dipole moment must change, but here must be polar. So hydrogen chloride, that's a polar molecule. Nitrogen is not. Chlorine molecule is not a polar molecule. Deuterium chloride is a polar molecule. Water is a polar molecule. CO2 is a symmetric, not polar molecule. So the answer is hydrogen chloride, DCl, and water. Question number 8. In the far infrared spectrum of hydrogen bromide, there's a series of lines separated by 16.72 inverse centimeter. Calculate the moment inertia and internuclear separation. Separation is the bond length. Okay, and we know that from rigid rotor, the absorption frequency is equally spaced, and the separation is 2bc in terms of hertz, or 2b in terms of inverse centimeter. So here is inverse centimeter, and therefore we use 2b. So 2b equals 16.72. And that gives you B constant. And then from B, you can calculate moment inertia and then calculate bond length. Or you can just use the equation. H divided by 8 pi squared divided by C divided by I. That's the B. Okay, so the unknown is I. And therefore, you can solve I, the moment inertia. All right. So with I, then you can calculate bond length if you know the moment inertia, the reduced mass, because this is reduced mass times R squared. So you need to find the reduced mass. Okay, and we have done this many times, so we skip this, and then we can calculate moment inertia. Okay, and so from this equation, R is square root, so square root I divided by U. mu. All right, so mu is this, I is here, plug in, that give you the bond length, 1.43 times 10 to the minus 10. Question number 9. The wavelength of transition from J equals 2 to J equals 3 rotation transition of hydrogen chloride is 63.56 inverse centimeter. What is the bond length? So this question is similar to the last one, but not exactly same. So last question, we use the fact that the absorption frequency is equally spaced. And the spacing is 2b in terms of inverse centimeter. But this question is not about the spacing, it's about the frequency. Okay, so for example, this is the frequency absorbed from J equals 2 to 3, and this one is J from J equals 3 to 4, and this is J from 4 to 5. So remember this, you have an energy level. And so from J equals 2 to 3, and you have absorption, the frequency is here, and this absorption frequency is here, all right? So what's the equation to calculate the frequency? Not the separation, but the frequency. And this is the equation we actually used in question 6. Okay, so 2b times J plus 1. So the frequency that will be absorbed depends on J. Okay, so that's why you have a series of absorptions. All right, so here that's 63.56, and J is from 2 to 3, so you plug in 2 here. 2 plus 1 is 3, 3 times 2 is 6b. All right, so calculate, and you can calculate the b. Okay, so from here b is 2. So you calculate the b. Now, what is b? b is h divided by 8 pi squared divided by c divided by I. So you calculate the I, the moment inertia. And what is I is the reduced mass times r squared. So calculate the mu, and then calculate the r. Now this is similar to the last question. So r is 1.26 times 10 to the minus 10 meter. Question number 10. Infrared absorption by hydrogen iodide give rise to R branch from V equals 0. What is the wavelength of the line originating from rotation state with J equals 2? So this is about infrared absorption. And we know that when we do infrared, it's always accompanied by rotation. So you will see broad peaks. And if we have high resolution, you will see R branch and the P branch. And so this is the frequency, and you will see many peaks first due to the delta J equals -1. That's called the P branch. And then you will see a bunch of other peaks, and this is delta J equals +1, and that's R branch. And we have a derived equation to calculate these frequencies. And for R branch, the equation is here. All right, you can find this from my lecture notes. And this is the natural frequency of the vibrator, and this is the rotational constant, and the J numbers from 0, 1, 2, 3. Okay. Now, how do you know the natural frequency of rotational constant for hydrogen iodide? Here is a table that you can find from textbook. So hydrogen iodide is here, so the natural frequency goes here, and the rotational constant. Okay, so here it says originating from the rotation state J equals 2. So from 2 to 3, that gives you delta J equals 1. So plug in J equals 2 in this equation. All right, when J equals 2, all right, so 2 plus 1 is 3, 3 times 2 is 6, and that's why you have frequency plus 6 times rotational constant. So plugging everything, the answer is 2347.2 inverse centimeter.